Hello, I'm going to present the paper Efficient Randomized DCAS for the 53rd Annual ACM Symposium on Theory of Computing. My co-authors are George Diakopis from INRIA, Mehrdad Jafari-Gif from the University of Calgary, and I am Philipp Wölfel. In this paper, we consider the standard asynchronous shared memory system. They are end processes which are completely asynchronous. So they run at varying speeds and may crash or fall asleep at any point. Processes communicate by executing atomic operations on shared registers. Registers are also called base objects. For this talk, we assume that these atomic operations are reads, writes, and compare and swap operations. And I will show you in a moment how compare and swap works. But for now, it's important to note that all these atomic operations are supported on most common hardware architectures. The compare and swap operation, or short CAS, is a powerful standard synchronization primitive. It allows a process to atomically compare a register with a value and change it to a new value if there's a match. The CAS operation takes three parameters: an address of a register and the values old and new. If the register's value at the given address matches old, then the operation writes new in the register and returns true. Otherwise, it returns false and does not change the value of any register. And all of that is, of course, done in one atomic step. For example, if the value of a register is x and the process executes a CAS with parameters a and b, then the operation fails because there is no match, and so the CAS operation returns false. On the other hand, a CAS with parameters x and y succeeds, so it changes the value of the register from x to y and then returns true. An operation we would like to have, but which is not supported by current hardware, is the double compare and swap operation, or short DCAS. It works similar to a CAS, but it affects two arbitrary memory locations. So the DCAS operation takes two triples of addresses and old and new values. For DCAS to be successful, the registers at the given addresses must both match the corresponding old values. If they do, then they both get atomically replaced with the corresponding new values. As the CAS operation, the DCAS also returns a Boolean value to indicate success or failure. We already said that DCAS is not available in hardware, but there are a large number of software implementations. This is because DCAS has shown to be an extremely useful synchronization primitive in a large number of applications. Some examples are a lock-free operating system kernel, transactional memory, priority queues, several double-ended queue algorithms, and other more general synchronization primitives. A problem is that even though many DCAS software implementations are known, none of them is very efficient. In all known algorithms, DCAS operations take in the worst case at least omega of n operations on base objects. And recall that n is the number of processes in the system. In this paper, we give a randomized algorithm for DCAS, and our algorithm is much faster than all previous algorithms. In particular, DCAS operations have an amortized expected step complexity that is logarithmic in the number of processes. Recall that all previously known algorithms have at least linear step complexity. We implement a data structure that maintains an array of values and supports the operations read and DCAS. But we can also easily execute standard CAS operations because we can simply use DCAS operations where one of the two addresses is a dummy location. Our algorithm does not support unconditional write operations. We believe that it may be possible to support write operations, but this is left for future work. Another restriction is that each successful DCAS operation must change both affected addresses to strictly larger new values. But we can simply attach increasing sequence numbers, and then it suffices that both affected addresses must change with a successful DCAS operation, but not necessarily to larger values. However, this still means that we cannot perform something that is called a double compare single swap, which compares two memory locations and conditionally updates only one of them. But this is a common restriction on most algorithms. Our algorithm is randomized, And so we assume that an adversary schedules the order in which processes take steps. The adversary is oblivious, which means that the adversary knows the algorithm, but it cannot see the random decisions that processes make. In our algorithm, processes can execute read operation on the DCAS object in a constant number of steps, and steps just means atomic operations on the base object. And DCAS operations have an amortized expected step complexity of O of log n. For our algorithm, we implement two building blocks. The first one is a repeated choice object that allows a group of interested processes to repeatedly propose values and then to randomly choose a winner among themselves. The other one is a bipartite version of the DCAS object called BDCAS. Here, the array of registers is partitioned into two sets, and now DCAS operations must affect one register from each set. We use the repeated choice object to obtain an efficient randomized BDCAS algorithm. And then we use that BDCAS object to implement our DCAS. In the remainder of the talk, I will explain the BDCAS and DCAS algorithms, but unfortunately there's not enough time to cover the repeated choice object. I will now explain the BDCAS algorithm. Recall that BDCAS works exactly as DCAS, except that the array is partitioned into two parts, a left half and a right half. Array entries affected by a BDCAS operations must be in different halves. We use an array R to store the entire state of the data structure. Each array entry stores a pointer to a descriptor. The descriptor contains a stat field. It also stores two triples of addresses, old and new values, exactly as the arguments of a BDCAS operation. If a pointer to such a descriptor is stored at a given address, then that address must appear in one of the two argument triples. The status of the descriptor is either old or new. Each array entry of R has an interpreted value. Consider the descriptor to which the pointer stored in an array points to. If the status of the descriptor is old, then the interpreted value of the array entry is the old value of the descriptor triple with a matching address. Similarly, if the status is new, then the interpreted value is the new value of the corresponding descriptor triple. Now suppose that we want to execute a BDCAS operation which aims to change an array entry on the left side from A to B and one on the right side from X to Y. Imagine also that the interpreted values at these addresses match. First, we create a new descriptor, the status old, and the same argument triples as in the BDCAS call. The goal is to write pointers to the new descriptor into array entries at the corresponding addresses. We say that we attach the descriptor to one of the two sides if we manage to store a pointer to the descriptor into the corresponding array entry. Once the descriptor is attached to both sides, we can change the status from old to new. This way, we atomically change the interpreted values of both array entries from A to B and from X to Y respectively. Now, how can we safely attach a descriptor? We have to be careful not to change the interpreted values when writing new descriptor addresses into the array. We will first check the left side address and determine the descriptor that is currently attached. This descriptor must belong to some other BDCAS operation. We will then help the process that created that descriptor finish its BDCAS operation by performing the same steps it would perform. The descriptor has all the information we need to do that. First, assume that while we help, the status of the descriptor changes from old to new. When the status changes, the other BDCAS operation takes effect. Because of that, the interpreted value of the left side array entry changes from one value to a different value. One of these two values is not equal to the old value we are expecting, which is A. So there's a point at which the interpreted value is not A. Hence, our BDCAS operation can simply fail and return false. Now assume that the status of the descriptor does not change while we help the other BDCAS operation. Our algorithm guarantees that the status will never change after that. We can then determine the interpreted value of the left array entry from the descriptor. If it is not A, the BDCAS operation can also fail. So now assume that the interpreted value is A. In this case, we repeat the same procedure on the right address. Similar as on the left side, our BDCAS will either fail or the interpreted value of the right array entry matches the desired old value x. So if our BDCAS does not fail prematurely, then at some point the interpreted value of the left side array entry is A. And at some point the right side array entry is x. We will now perform a CAS operation trying to attach our descriptor to the left side. That CAS operation may fail because some other process may have already attached its own descriptor instead. In that case, we may have to start over our entire BDCAS operation. However, we are guaranteed that if the CAS is successful, then it does not change the interpreted value of the corresponding array entry. If the CAS succeeds, then we repeat the procedure on the right side. If both CAS operations succeed, then we have successfully attached our descriptor to the left and right side without changing in any interpreted values. Thus, we can complete our BDCAS operation by changing the status from old to new. Our BDCAS operation has taken effect and can return true. We have just seen that adding descriptor pointers may require that we help other processes finish their BDCAS operations. Moreover, we may have to restart our own BDCAS operation if one of our CAS operations fails. First, observe that we always first try to attach the descriptor to the left side, and only if that is successful, we try to attach it to the right side. So if we ever successfully attach it to the right side, then it is attached on both sides. Hence, all that is left to do is to change the status from old to new, and so our BDCAS operation is guaranteed to succeed. Note that other processes will try to help our BDCAS before attaching their own descriptors. Now suppose our CAS operation on the right address fails. This can only happen if some other process's CAS operation succeeds. So that process must have successfully attached its own descriptor. That other process's BDCAS operation is then guaranteed to be successful and will eventually change the interpreted value on the right side. When we start over with our BDCAS operation, we will eventually see that there is no match to our old value on the right side, and our BDCAS can return false within a constant number of steps. So the problem is really only attaching our descriptor to the left side. Whenever a process has achieved that, its BDCAS will finish within a constant number of steps. In this drawing, each edge corresponds to a BDCAS operation, and its endpoints are the affected array entries. Now consider a scenario where there is no contention on left array entries, but high contention on one right side array entry, on which many processes want to perform their BDCAS operation. In this situation, all processes will quickly manage to attach the descriptors to the left side. Then one of them will be able to successfully attach its descriptor to the right side, and that process's BDCAS succeeds. So all other processes will fail to attach themselves to the right side. But the successful BDCAS changes the interpreted value of the right side array entry. And so all other BDCAS operations with the same right side array entry can fail and return false within a constant number of steps. So high contention on a right side array entry really is no problem. The problematic scenario is the one depicted here, where many BDCAS operations share the same left side address. Only one of the processes will manage to attach its descriptor. All other processes' CAS operations will fail and they have to start over. The idea is now that all processes competing for the same left side address will choose at random who among them should be successful. This is facilitated by our new repeated random choice object, which I mentioned earlier. Suppose the random process successfully also attaches itself to the right side. Then its DCAS will eventually succeed. Therefore, the interpreted value of the contended left side array entry changes, and all other competitors for the same left side array entry can finish the operation and return false. So the adversary must try to prevent this from happening. And the only way to do this is to speed up another process that will attach its descriptor to the same right side as the one of the randomly chosen process. But the adversary does not know which one the randomly chosen process is. So it has to attach many other descriptors to cover many of the right side addresses. As a result, many of the DCAS operations with the contended left side address will be able to finish and return false, because the interpreted values of their corresponding right side array entries have changed. It is not hard to show that a constant fraction of all of the DCAS operations sharing the same left side address will make progress. This yields an expected amortized constant step complexity for DCAS operations. But this assumes that we can actually choose a random process on the left side in constant time, and that is not true. In fact, our repeated random choice object allows us to do that only in logarithmic time, and so the DCAS algorithm also has logarithmic amortized expected step complexity. I have shown so far how to construct the DCAS algorithm with logarithmic amortized expected step complexity using the repeated choice object. In the next part, I will show you how to use any DCAS object to implement a randomized DCAS algorithm. We will represent the DCAS object with a DCAS object B, which has twice as many array entries as the DCAS object. In particular, each array entry of the DCAS object is represented by two array entries from the DCAS object, one from the left side and one from the right side. We will use descriptors again, and each DCAS array entry stores a pointer to a descriptor similar as before. At each DCAS address, there are now two descriptors attached, one in the left DCAS part and one in the right DCAS part. Our algorithm will make sure that the corresponding interpreted values always match. This way, the interpreted value of the DCAS array entry is uniquely determined. To perform a DCAS operation, we will create a descriptor describing the operation as in the DCAS algorithm. Our goal is now to attach the descriptor to the four DCAS entries that correspond to the two affected addresses of our DCAS operation. If we succeed, then we can change the status of the descriptor from old to new. This will then instantaneously change the interpreted values of both DCAS array entries as desired. Before attempting to attach our descriptor, we will check all descriptors in the relevant DCAS array positions and help the corresponding DCAS operations finish. If that changes the interpreted value of an affected array entry, then our DCAS operation can fail and we return false. Otherwise, we perform an attempt to attach our descriptor simultaneously to two array entries, one on the left side of one DCAS address and the other on the right side of the other DCAS address. Note that this can be done with a DCAS operation. The DCAS operation may fail, because in the meantime some other process may have attached its own descriptor. If that happens, we have to start our DCAS operation over. Our algorithm guarantees that if a descriptor gets attached anywhere, then the corresponding DCAS operation is successful with constant probability, and thus changes the interpreted value of an array entry. Hence, whenever we have to start over, with constant probability, we can return false. As a result, after a constant number of steps in expectation, we will either have attached our descriptor or our DCAS operation has returned false. So now assume that we have successfully attached our descriptor. Our next goal is to also add pointers to the remaining 2 BDCAS array positions. We will attempt this separately for each address. Let us consider the DCAS entry with index 5. We will have to replace a pointer to a descriptor that belongs to a different DCAS operation. If that DCAS is not yet finished, then the calling process may also want to replace our pointer in the neighboring BDCAS array entry with one pointing to its own descriptor, while we are trying to achieve the opposite. So instead of both processes stealing each other's pointers, they will at random choose a winner among them too. The loser will then help the winner attach itself. So both are performing the same steps to replace the pointer to the loser's descriptor with a pointer to the winner's descriptor. With constant probability, we win this random competition on both sides, and thus all 4 BDCAS array entries point to our descriptor. In that case, we can just change our descriptor status and our DCAS takes effect. So if we manage to attach our descriptor, then with constant probability our DCAS will return true within a constant number of steps. Earlier we showed that in constant expected time we can either attach our descriptor or return false. Thus, using a BDCAS array, we can implement a DCAS array with constant expected step complexity. So, I have shown you how to use a repeated choice object in order to obtain a randomized BDCAS object, which can then be used to obtain a DCAS object. As a result, we can implement a DCAS algorithm from read, write, and CAS operations, where DCAS operations have O of log n complexity against the oblivious adversary. There are a number of open problems. For example, whether there is an efficient deterministic DCAS algorithm with sublinear step complexity, or at least a randomized algorithm against an adaptive adversary that can see the results of coin flips. It would also be nice if we could support write operations, and this may not be super difficult to do. A very important open problem is to support double compare single swap operations, which would allow processes to compare against 2 array entries, and if both match, to change only one of them. And of course, there's the natural question if this can be extended to KCAS for k larger than 2. This operation is like a DCAS, but it supports operations on k registers instead of only 2. That's it for now. Thank you for watching this presentation and enjoy the rest of the conference.